Is that a question?
Yeah, it is a question. And the answer is always, yeah, I'm about to drop some knowledge.
No, I'm going to guide you through the beauty of the science, okay?
Through a 3-course meal?
Much less.
All right, let's get back to the topic today. So, there's not much class left. There's only 3 classes. So, save your time and enjoy the last 3. Yeah. So, it's approaching to the end of this polymer physics class. But our interest in the science never stops, isn't it? So, what we're going to do today, I feel a little bit dark. No, it's cold outside. Let's turn on the light first.
It's like a creepy wind thing going on out there. Yeah.
All right, let's talk about science. So what we're going to do today is continue to talk about rubber elasticity. So last lecture, we only touched a little bit about what is rubber elasticity is. So in today's lecture, we're going to go into discuss what's the difference between the rubber elasticity for polymer versus metal. And I'll convince you why rubber elasticity is very much different with metal elasticity, okay? In the next lecture on this Thursday, we will cover a bit more into the science aspect. If today's lecture is a little bit, if today we haven't get into the single chain statistics of the pulling the single chain spring, okay? So what we're gonna do today, today's goal is actually to understand rubber elasticity from a thermodynamic perspective, okay? So we're gonna again talk about the first law and second law of thermodynamics and understand how does the force can be correlated to the formation of the chain. So can anyone help me with the first law of thermodynamics? What's the first law? Huh?
The law of conservation of energy.
Yeah.
After P is always increasing, is that the
That's second.
No, that's second. So we can just say a general idea of internal energy, okay? Internal energy of a system. The first law basically tell you if you apply the work to the system or you change the heat to the system, you will change the internal energy, okay? So this internal energy of the system, U can be changed by 2 ways. First is adding heat or work. So if you think about a car engine, it basically converts the heat to the work, right? So if you write delta U, this is change of internal energy. When we talk about the delta H, delta H entropy, enthalpy, we didn't talk about external force. So today's class, we will consider that into this equation, dq. Q, we can say this is going to be heat exchange. F plus dW. W is going to be the walk. How much force per distance you gave it to the system, right? So this is going to be the walk. So what this general, very general first law of thermodynamics tells you if you has applied the heat into the system or apply the work into the system, your internal energy is going to change. Good. So
You can see the beauty now.
that's the first part of it. Be patient. We haven't got there yet. So how did you quantify how much work you gave to the system? Or specifically, how would you express dW? How much work you're giving to a closed system? Think about a general case will be force times distance that would be one. And the other one, more generalized in the first thermodynamic law, is pressure multiplied by volume change. Okay, pressure dV. So we can just generalize to be this equation, like Nathan mentioned. This would be the force, and this would be the distance. So if you apply a force for a certain distance, you generate the work. If you only apply the force, there's no movement for the object. You don't generate any forces or works. You have forces on, but you don't have works, right? Same for the first term. This is the P as pressure, V as volume. So if you have a pressure generate displacement of volume, think about a car engine, then you generate work as well. So in this very general equation, we link to what the dW is related to the force distance. Okay? And why we care about this? Because while you deform a rubber string, we need to consider what is the entropy and enthalpy change into one system. So we will soon get into that step, okay? But these need to be lay a foundation for what we are talking about next. This is basically the first law of thermodynamics. Okay, there is also a second law which talks about for the difference in the delta Q. In this heat exchange is related to the enthalpy. It can be generalized or written as ds dt, or more commonly, people would prefer to write it as dq in this way. So if you combine this du, the total internal energy, you can generalize this a way to write T ds minus the pressure okay. So this is some of the fundamentals for thermodynamics. So your total internal energy is equal to the temperature difference multiplied by ds in your system, and PdV is the work done as well as FDL. So that's the total of work you did into your system. Okay. So how does this going to be related to the later on part? Because we now can connect what we have been all know, delta G, this we have taught many times in the second chapter 7 for the thermodynamics of mixing, where delta G is related to the delta H and delta S, right? So if you want to expand this a bit, understand the difference between individual parameter, you can write as this, expand to be U, as again internal energy, PV minus PS. If you just write a G equals to, okay? So that's a total free energy for the system, going to be related to the internal energy, pressure multiplied by volume, temperature multiplied by the entropy difference. Any question for this part? It's just the fundamentals of the thermodynamics we're talking about. But this can be linked to what is delta G can be related as a derivative of delta G will be equals to, we can write it as dG equals du plus derivative of PV going to be dP multiplied by V plus P dV minus dt multiplied by S minus T. So what we did is just take first the derivative of, or tell that what is dG. dG is small changes in delta G, okay? Small changes in the free energy are going to be equals to du, dP, dV, dt, ds. So as you know, in the changes, we can basically transfer this to the du, because they have shared quite a lot of terms. For example, we have PdV. So if we link these two through this part and TdS, we can correlate these two parameters. If we do that, we will get d delta G going to be equals to V dP minus S dt. So doing this way, we kind of linked what is G versus force. So you can use this to correlate the free energy versus the work you did into the system. Okay? So what does this mean? This equation can be further linked to partial derivative. We know what would be the V to be. V going to be, if you take partial derivative of G versus P, right? At the fixed temperature as well fixed L. So how we get this? Because we can move it to here, and while we fix the other two terms, if we don't have changes in L or T, these two terms will be 0, right? Similarly, we can get what is F will be. The force applied to the system will be equals to G dL at constant pressure and temperature. So the little sign on the corner means it at constant pressure and temperature. Some of the fundamentals of the thermodynamics in this class regarding rubber elasticity is, if we want to know how much force is being applied or how strong your rubber elasticity is, we need to get the delta G and know how much deform we gave to the system. Then we can get this force. Okay? So that's where we want to aim for today. What is delta G and what is delta L? And that will give you rubber elasticity, or the force applied to your rubber. Okay? So that's a key thing. We need to know the force on the rubber material. Specifically, how would it be different? And it's a question we want to know. If you think about, you pull a rubber or rubber band with your hand, you pull it, it's going to deform, right? You changes L, or the distance of the rubber string, So if we have, say, this would be the piece, we pull it, it will be deformed by a certain amount. So in this changes, you're going to change the many things, right? You're going to potentially change the entropy aspect and also enthalpy aspect in between different molecular. Okay? So let's take a look more details how these would be if we expand this forces. What is F relate to delta G? We can see there's actually two terms into it. And this difference, this differentiate what is between a metal and P and T, okay? So the force you apply to a system is derivative of G and L. L is displacement, G is free energy. So we know this is basically delta H minus P Why we need to care about this? Because now we're speaking about what happens on the molecular level for deformed rubber versus metal. So you will see in the next 20 minutes, this term is enthalpy contribution, which is dominant for metal. And I'll spend the next few minutes to explain why this is dominant for the metal for this first term. Well, metal doesn't have much entropy while you deform it. So delta S partial derivative L is almost non-change for the metal. And you will see a general term, entropy contribution will be dominant for polymer rubber, okay? And these are potential two of the contributions to your system. And let's take a look. Now, I want you to imagine you're holding a piece of metal and you start to pull it. What happens on the atomic level to the metal? Think about this like a very nice gold necklace. You're still pulling it. What happens in the atomic level? Why is it being deformed?
Putting strain on ionic bonds.
What bond?
You're putting strain on the bonds between the individual atoms.
Yeah, there's, but most of what you're saying is correct, but there's no bond, right? There is just interaction between each individual atoms, right? So if you think about what happens on the atomic level, so each circle represents a gold lattice. So while we deform a metal, as an example, what if we pull it? Again, this is going to be a metal bar. If we pull it to make it deform, to be longer, okay, this is original length. We pull it deformed. What happens on could be on atomic level is where you now starting have the lattice start to shifting, because there's no covalent bond between each individual atom. What attracts them is, van der Waals force, or we can generally plot it as the energy versus atomic distance, right? So we can have the energy for the system where we have inter-atom distance. So what would you think the energy would be look like in generic term? If two atoms are very far away, what are they going to happen? What kind of force they have? Attractive force. So that's like generic in, it dominates, for example, in gravity, where these are the forces you're going to have. So let's call a 0. And this would be attractive force. So at very far away, you're going to have very tiny, almost close to 0 attractive force, right? While you get distance start getting closer, your attraction will raise up. And once they close to the atomic distance, we can define a new term called R0 is atomic distance. Your force will reach a maximum, right? In this, you can understand why there's a rapid increase in the attraction force. And fast past that, you're going to have a repulsive force. That's basically how these atoms works, because you cannot occupy the same space. If you force two atoms to get very close, there's going to be a lot of force repulsively. So for the metallic material or other material, what dominates for the interaction of the material is inter-atom force. So you think about these are attraction or repulsive force, while the entropy term for the metal is very little, because it's still pretty ordered after you deform them. You know, if you shift this row a little bit further away, they're still pretty crystalline. So you wouldn't expect there much change in delta S while you deform a metallic material. Okay? So now coming back to what we talked about. If you have spring of metal, metal spring, okay? It exists almost universally in our life. If you buy a new car, that's in the anti-vibration system, or in some of the pen, you have a spring, a metal spring right there. If you deform this spring in the original phase, if you compress it, it will exert a force to that, right? So this force, or spring force, is related to this intermolecular interaction. If you compress the spring, you are changing the distance of two atoms, okay? That's resulted in difference appearance to macroscopic force F. So, for example, we can get a generic term for what this energy could be, right? It's almost is a parabolic shape within a small range. If you have small changes in distance, it will rapidly raise, right? So you can basically get, say, if the metal deforms slightly, you can get this force, or the slope of this, going to be your force, or the spring constant, because you deform the atom from R to, for example, here to R1. If you move it this from the peripheral lowest energy state to, for example, a distance slightly further away to R1, you're going to have more attraction force coming on. That will result in different forces in your material. Okay? And this R1 tells you how much slope of this material will tell you how strong this attracts or repels your material. And we can actually know the slope of this would be force. Okay. That's dr. That's the small difference in the horizontal axis. That's vertical axis. So that's basically tell you the slope of this material, of this curve will tell you what's the spring constant for your spring, or metal spring. Okay. So why does this matter for us? In this case, you can generalize as U, or we can call this U energy. You can generalize U would be a function of rate r. The distance between two corresponds to r minus r0 squared. This you can think about a constant value. R is where the distance between two atomic molecular. R0 is where the lowest is the energy state. So if you plot this, that's what you would expect, right? This would be the R0 where you have lowest state. So if you look at in a small deformation here, that can be described by this function. That's the energy for a metal atomic molecular while you shift the one atom a little bit away from each other, and how much force you would get as a response. And we can know, if we do this, a simple calculation, you can get the value of this would be 2c r minus r0. And we can envision this would be written as a strain for atomically, right? So the deformation of strain would be the new position minus original position divided by R0. That will be the strain of any deformation. So if we understand this, we can get 2CR0 multiplied by strain would be what is the force exerted on that. And you can get elastic modulus would be stress divided by strain. We know what the force is, right? And we can divide by a cross-section area, A, divided by strain. So you can see that would be your spring constant of shifting atomic molecule away from what is an optimized position. Okay? So if I could, being a very, very tiny nano man, I dive into the world of atomic world. I shift the one atom a little bit away, how much I force need to change that, which is given that equation, okay? So that gives you what it needs to deform the metal. It is dominated by entropy term, because they're talking about energy difference. Is it attractive or repulsive while you pull two atoms away? Any questions so far for this part where we talk about metal? Yeah, please?
The repulsive force is just
Yeah, yeah. So in the local scale, think about if that is another gold atom as a protein right there, and the other one, in the crystalline material, let's say, they would be happily about a meter away, like this. And at another meter, there are going to be another crystalline gold atoms right there. And this would be the lowest energy state. Everybody is happy. So if I get closer, I got a repulsive force from my neighbor. If I get a little bit far away, I got attraction force, right? That's basically where this lowest energy, or this while is. Now, going either way, I will get increase in the energy. Okay, so that's what happens in the metal spring or in your pen. Is while you change it, it changes the inter atom distance, and that's affect your elastic modulus. Okay, so the system want to go back to where it's at. Think about now. This is if nothing going on, you have a spring in your pen. That's where it is. If you let it go, there's no force applied to that. If I press the pen down, the distance at the molecular level changes. I gotta go in here. There's more repulsive force, so the spring wants to restore it back to its state. Purely entropic. Okay? All right, now, since we are a polymer science department, we have to talk about what's the difference for polymer. Let's come back to this equation. In the ideal elastomer, which you can think about as in this case, there's a network where you have bonds, right, connected. While you pull a rubber band, what you deformed is the chain between these two strands. If we only magnify here, this is the before pull. If we do the deformation, that will be after. What's the difference between this picture and this molecular picture?
All the points are bound.
Well, the points are bound. Oh, we are looking at something that a little bit bigger than atomic scale, right? On the atomic scale, there's a little bit rearrangement of your molecular structure. But clearly, in this case, if I am the atom, the distance of between atoms is not changed. So not like in this case where the distance is clearly changed. So we usually say for ideal elastomer, delta H Pt is equal to 0. What does this statement say is there's no entropy changes while you deform an elastomer. And is this assumption more or less correct? In most of the case, is very much close to the reality. Okay, what do I mean by that? We can actually test a rubber band by pulling it. So if you have a rubber band, you can plot as stress and strain, or this can be elongation or the strain. And this you can plot as the stress or the force. Okay? What you typically see is it's almost a linear increases. It's very much similar behavior than the rubber spring, but the intersection of the distance, you got a delta H. Or if you want to separate two, the delta H per L for a rubber band is more or less constant. If you take a derivative of that, it will not have a slope, so it's more or less stable. But what this contributing to the force is purely coming from the slope, and that's the entropy contribution, okay? The slope is the force, or F. So any question for this part where we talk about what the difference between the metal versus the polymer case, where you actually don't see much changing here. The contribution is mostly the entropy difference. The entropy difference is what we're going to talk about once we get a break, is delta S difference. S means the entropy. So before you pull this rubber band, your polymer can have many configurations, right? And we know S equals K log n, the potential number of different configurations. So if we get this, what the S value are,
so there are fewer configurations when it's stretched.
exactly. While you have the chain, I can give you an extreme case. If you have a rubber band, we know the end-to-end distance for a polymer. We can calculate that with a known distance, right? So if we pull the chain fully straight, the number of configuration is going to be one configuration is every chain is straight. If we give a little bit of room, you have a few more configuration. If it's in the undisturbed condition or where unstretched, you have the biggest is the entropy. So let's take a break. After we came back, we will look what this value will be and how the delta S difference before we pull the rubber band and after we pull the rubber band. And that's pretty much will tell you what is the elastic modulus you would get from the ideal Gaussian chain while you pull it. I again going to be the nano man. I'm pulling one end of polystyrene while the other end is fixed in the wall, or Nathan can give me a hand to pull the other end. Then we can know how much force we need to pull a single polymer chain. Okay? Let's take a 5 minutes break. Then we come back to what is delta S is. Mm-hmm.
I'm still writing that.
Okay, I can restore it for you. That's gonna be so this part contribution is more or less similar. That's okay, and that would be the deformation line. Hmm?
So we're a lively bunch today.
I don't know what happened to you guys. Looks like everybody has just finished their marathon yesterday. Maybe the weather is directly proportional to the energy.
I haven't seen the sun in like 4 days.
Scientific fact that the sun
Doesn't exist
improves
anymore.
mood. Okay.
Mm.
Not time for exercise. It's too much
No,
studying.
it doesn't exist. I was thinking improves mood. You get energy.
That vitamin D. Vitamin D3, D2 useless. Difference between D2 and D3. Different precursors. D2 is a plant precursor.
Okay.
Part of your body metabolizes.
All right, let's get slowly back to the class. So, in the first half of the class, we discussed what using a thermodynamic aspect, what's the difference between deforming a metal spring versus a polymer. The conclusion is coming from the fact that the major difference is coming from, is it an entropic contribution dominance, which is the case for the metal, versus entropic dominance, which is for the rubber band. So the next half is we're going to see how much delta S is difference. So if we know, if we can solve what delta S is, we know what would be the forces, right? So then we are golden for this part. Okay. So how about what is number of state for a polymer chain before and after deformation? So in this case, I kind of arbitrarily say I'm going to ping one of the polymer chain in to the origin of your axis. Okay, that's where the origin is. That's the other end of the polymer chain. After we pull it, we're going to reach a new distance, right? Because we deformed it. So the origin of your chain end, we can always say it's going to be 0, 0, 0, because you manually stick to the origin of your axis. And this, we can say x0, y0, z0. Once we deform it, we call it x, y, z. Right? Then you can see if they equals to each other, we didn't deform your polymer chain end. Right? So that's a before, and that's after deformation. The difference between these two. Oh, now the question is, how can we get this value? How do we get this value? Number of different state. And we roughly spoken, after deformation, this value will be totally different. Right? So what is this value would be? Any help? Factorial, that's related to what is law in this state is. What we did it before is your law in this state you can get. I want to point you guys back to now the chapter 6 where we talk about chain end distribution. The probability of chain end distribution for a Gaussian chain. So in this case we can probe the problem by understand what's the probability of distribution before and after. Why this matters? Because after we deform it, the number of state is directly related to the probability of distribution. And can someone help me? What would be the probability of distribution is? We can write it as a function of n and h. H would be the end of end-to-end distance. Okay, n is degree of prolongation. P is probability. Anyone recall that long equation I desperately need some help. Because I don't remember what the probability of distribution.
It's not the p equals 3 over 2 pi and b squared is 3. Is it that one?
Yeah.
Okay.
With the beta?
3 divided by 2 pi and b squared raised to 3 halves.
That's what we got.
Exponent negative 3 into n distance squared divided by 2 and b squared.
This looks like a very lengthy, long equation. It is, yes, of distribution when you have h. So let me write down. Probability of n to n distance is equal to h for a Gaussian chain of has mb square and root n to n distance. So that's equilibrium n to n distance. N is degree of polarization. B is we call the Coulomb monomer length, or basically mb square is a Gaussian chain, right? mb square would be what's the distance if it's right in that range. Okay. So what does this equation? Can someone help me? What does this equation do? So let's look at what is this part. What is the first part of this equation? We haven't worried about this part yet, but look at this part. 2 pi mb square, and the bottom 3 is on top.
Number of configurational states that it can be in as far as like trans or gauche. Is that right?
That's it's not what I'm asking specific for this one.
It's like the radial unit of like all the spaces it can occupy.
Pretty close. This is a normalization factor for the distribution, because for a given material, we know 2 pi, that's a constant. It doesn't change it versus the h. Right? H is the changing factor. So 2 pi mb square is a constant. This will be a constant. Power of 2/3 is a constant. As long as you know what is mb. So for a polymer, know its degree of polymerization, know its b, you know what is going to be distributed, right? This will be an ideal case, let's assume, where it's starting from.
In practical senses, your B will change based on like the solvent or your concentration or
Right,
all sorts
right.
of factors.
So B will change only if you're talking about immersing or changing solvent while do stretching. But in this case, we just talk about, again, in the vacuum, you just have one chain, and now you start to stretching one chain.
Okay.
Okay. So this will be a constant, and it's not going to be changing with any part of your structure. So 2 pi mb square 3 divided by this value will not change. How about this part? E power of 3 h square. How about this part? Well, it changes as function of n or h, and how do they relate to that? So this tell you, first, everybody know what the E minus X will plot like, right? It will decay rapidly versus x. H is the distance of end-to-end distance. So if we plot this p as function of h, what we will see is it has the highest chance you find end-to-end distance to be mb squared in the Gaussian chain. Okay. If you find distance is shorter than that, the chance is much lower. Neither the case once the distance is higher. Okay, it's a probability of distribution in end-to-end distance. So help me out in here. H squared will be end-to-end distance. MB squared will be ideal end-to-end distance. So this is just a function of end-to-end distance. And as we say, the probability is going to change with that. Okay, so why does this matter to us? It matters that while you deform it, you are reaching a low probability of state. So your entropy will go down dramatically for your system. It's relatively proportional. We can use this to determine what S is. So let's call one condition. Let's have it say what would be the generic state for the entropy. So we can write this down. S will be k ln, and this can be given by a constant multiplied by this probability function. Okay? So the higher probability means your entropy is bigger. The low probability means your entropy is very small. Let's do that. K ln a very long equations. We have 2 pi mb squared. We're going to repeat what we have there. 2/3, and they're going to be E h squared 3 2 mb squared. So can someone help me with this equation? What's the k ln this very long equation?
What is K?
K is a Boltzmann constant. K.
What's the question?
What is ln this value would be? Because if we can know what the values are, we know the entropy difference before and after, right? So in one state, we can expand this. Ln A multiplied B will be equals to ln this value plus ln the second value, right? Or what we have is ln A is a prefactor, we just talked about here. E is exponent, B is the value here. So this will be equals to ln A plus B. That's just the mathematics, but it is, right? Let me do it one more time. And in the center, big enough that everybody can see. Ln A exponent B, or even simpler, ln A multiplied by B will be equal to ln A plus ln B. Right? Simple math. So in this case, it's going to be ln A plus ln E B. And this, we know it's going to be equals to B. So it's going to be ln A plus B. Okay? So let's work on this a little bit more complicated equation. This is going to be equal k to pi mb squared. We're going to get this figured it out just in 1 second, plus 3h squared to mb squared. Correct? And we know, as we talk about, the first factor is nothing decided by the h. So we can just call it a constant value. If we know what is mb, if we know what is n and what is b. So the first part is constant, okay, which is this part. The second part is 2mb squared divided by, not divided by, multiplied by 3k h squared. So what we can see is the entropy S is always equals to roughly proportional to what the end-to-end distance h is divided by mb squared. So if we start to pull it, Ansley, question?
Did you drop a negative sign from our probability equation from what's in the x?
Oh, right. There is a minus sign. Thank you. Okay. So that's what we get for what is S relationship with H. So it tells you a lot how does entropy relate to what is H squared is. Entropy will decrease if you start to pull the chain away. Now, let's really get what is delta S is. We know what is before and we know what is after before we pull the chain, right? So now why don't we get the delta S or the entropy difference while you pull a polymer chain? So we call it S initial, where we start before we pull the polymer chain. Excuse me. And once we pull it, we can have S final, or the entropy in the final state for your polymer chain. Okay? So what it will be look like? Delta S would be S final minus S initial. The final state of the chain minus what is happened to the initial state. So what is this final state? We need to know what is final state h squared or end-to-end distance square, right? Hmm? Is it smaller or bigger if you think about end-to-end distance if you stretch?
If you're stretching and increasing the distance, you're decreasing the entropy.
Right. So what we need to get is what the S final first is, right? In the final state, what would be the end-to-end distance? So the h will be equals to xy squared plus xyz squared, right? It's just a simple mathematics. If you have three-dimensional distance from one point to the other, which is end-to-end distance, can be equal to x squared plus y squared plus z squared. xyz squared equals to end-to-end distance squared. We can call it a final. And what would be the initial? It's going to be x0, y0 plus z0 squared. That will be the initial end-to-end distance, which is determined by x, y, z. because the other end of your chain is at origin of your axis. So you can very much simplify this process.
Does your B change? It should, shouldn't it?
No, it should not. For a given polymer, your cool monomer length should be fixed at different degree of stretching. All right. Now, I need a volunteer to help me with this equation. Otherwise, we cannot finish it. Everybody is going to stay for the class. Someone?
So what do you want me to say?
What is delta S?
I mean, you just write the same S function but with different H's.
Right. So you're going to have initial or the final state of entropy, which will be a constant, right? This does not depend on how you pull it, because all these values are going to be a constant value, right? And it's going to be minor 2mb squared h final, where the end-to-end distance final square, right? Minus another big box is going to be, again, in the initial state constant, minus 2m.
Constants are different than each other, though.
They are
Be-
the same.
they're the same.
Let's go back and I'll explain why they're the same.
So you can just cancel like
Yeah.
most of this.
Right.
Okay.
That's the whole point.
You-
So delta S is just the
H final minus finish.
minus H initial squared.
Right. So, no, it's actually the other way around, because it's 2mb squared 2k h initial square minus h final square. And this is a constant, and we have 3 multiplied by k. K is a constant. You write it more clearly. Okay? So the delta S, before and after you stretch a single polymer chain, is given by what would be the end-to-end distance difference before you and after you deform them. And we can even know a bit more in what is h squared value is, right? What would be the h squared value are?
That x squared plus y squared plus z squared.
Hmm?
Your equation up there.
So that's is something we can take advantage of, right? So, what you would have ended up is initial x0 square minus x square plus y0 square minus y square plus z0 square minus z square. This looks like a little bit lengthy equation, tell you what the entropy difference. So if your polymer is not deformed, the final state and initial state will be exactly the same. So your delta S will be 0, so no difference in entropy. While your axis increases now, all these three will be contributing in your entropy difference. We can consider a case where we now can actually define a Joule ratio, okay? We talked about what is Joule ratio. Joule ratio is defined as lambda will be equals to final state of L divided by L0. L is after deformation, what the length in your material is, and L0 is before deformation. So if you pull your material twice of its length, lambda will be 2. Okay? That's what this lambda is. You can also apply to that, where in the deformation, we can define several cases. We can call it lambda x. Or in the x direction, how much deformation you have. We can define as x final divided by what is value of what is x initial. So that's a Joule ratio in the x direction. You can do this for the y, and you can do it for the z direction. And this would simplify this equation. Daniel, you want to help me? Not today?
Sorry.
I was hoping you can give me some help.
PP equals nRT.
All right. What if we apply these values in? So, what you would get is now, what is lambda x versus x0, right? X gonna be equals to lambda x, x0. So you would get lambda x squared minus 1, x0 squared, and do the same.
Seems like it makes it a lot more complicated.
You will see it's gonna get clear.
We're all gonna end up canceling.
Trust the guy, guys.
Something beautiful.
Are we at dessert yet?
You guys are spoiled. It's not dessert time yet. There should be okay. Okay. Does it make sense? Does it make sense to everyone what the delta S is?
It makes sense, but I don't get where you're going with this.
Where are we going for this? Very good question. So if you have a rubber band, if you want to get theoretically what is the force versus displacement curve, you can get it with theoretical argument here. So at the beginning of the class, we talked about what would be the force related to the entropy, partial derivative L, or force will be. Okay? So if we could get what delta S is, which is we already have, we can understand how this would relate to the lambda. And that will give you a theoretical explanation what is for stress and strain curve for ideal rubbery material. Does it make sense better?
Yeah, that makes sense.
All right, we're going to have one more step, then we can finish today's class. So what the next step is, what if we consider an ideal rubbery material? Because in this, we talked about just a chain at atomic scale while you start to pulling it. In a piece of rubber, while you deform the rubber, you will have deformation coming from different aspects, right? So now we are looking at the macro scale. This would be L0, this would be L. So the draw ratio would be L divided by L0. That will be your lambda in x direction. Right? Let's call this would be, that's just a unifying with what we talked about there. We call it y direction in this way. That's going to be the difference in the final versus the initial. So how about if it is an ideal elastomer, what would be the lambda x and lambda z in the other two directions?
Height and width?
Yeah. So if it's ideal elastomer, we know there's no deformation. So, or this material is incompressible. Right? So if you pull a rubber band, it will elongate in one direction and shrink in the other two directions. And the value of shrinkage is called Poisson ratio. Okay? And in the other two directions, what do you get will be 1 divided by lambda y. Okay? There will be the similar. In other words, if you deform twice the length in one direction, in the other two directions, you're going to shrink by √2. Okay? Make sense? Everybody? Now, since we know what are the individual lambda x and lambda y and the lambda z correspond to a generic deformation ratio, we can start to simplify our delta S here for ideal rubbery material. So what would be the delta S for ideal rubbery material?
Wouldn't it just be 0?
No, apparently it's not. Right? Because for the rubbery material, if you pull it, there's different in delta S.
Could you plug in 1 over lambda for the pick one of the lambdas to be your original deformation, and for the other lambdas, plug in 1 over lambda?
Great, let's give it a try.
Awesome.
Michael.
I'm excited.
So what would be the values once we consider the ideal rubbery material? Let's actually do it here. What it would be?
What would it be?
Yeah. What would be the delta S
All right.
for
Delta S. Let's start there. There we go.
for a rubber band? Okay. After we
Deforming in the x direction?
we can in this scenario or this geometry we just call it the y direction.
So then you would still have 3k in there, for sure. Right?
Yeah.
So for lambda x squared, it would be 1 over lambda y.
And looks like we know what is lambda x y z is
We know what lambda x y z is.
for a rubbery material.
Can we start
Right. So what if we know it's an ideal elastomer? If we pull in one direction,
The others are shrinking.
it's going to shrink in the other two directions. So that's what the deformation for each direction is. What is lambda y, lambda x, lambda z. So what we talk about here is very general, not necessary to be a unidirectional pull. It's like generic what the delta S is. Now we move into the case where it's more specific. What if it's tensor, one direction? That answers your question, why we bother doing the equation here. Because the theory precisely predict a natural rubber elastomer, if you pull it, what's the force versus displacement curve. It matches perfectly with the theoretical description. Okay? So what we need is, this part is now lambda x. It's equals to 1 divided by root of lambda, right? We know what is lambda y is.
1 over lambda.
Lambda y is just going to equal to lambda. We know what is lambda z is.
1 over lambda.
1 over root of lambda.
But it's squared.
Yeah,
Wait, why is
So like, can you cross stuff? Can you pull things out? Just
right.
simplify all the lambdas.
And the other thing we haven't solved is what would be the x0, y0, and z0 would be.
1, 0, 0, 0.
No. Before,
That is.
before you deform. So in this case, what we talk about specific is a rubber band before and after you deform them. So what we had for the x0, let's first write it here. It's going to be equals to y0 square will be equals to z0 square. Because in ideal cases, it's equal distribution in all directions. Right? If you have an initial state of a rubber band without deforming it, your end-to-end distance is equally in all three directions, x, y, z. Before you pull the rubber band, it should be equally probable in the end-to-end distribution in all directions. And we know the h square is going to be mb square. That's the end-to-end distance. And we know there is another connection right here, h0, before deformation. Question?
Does this all cancel out to 3K?
No.
What happens?
No.
Okay.
No. Be patient. We're going to be there in 5 minutes. Okay. Really? I thought it's fun, huh?
I thought I knew where you're going, but now I'm
It's like
lost
a
again.
murder mystery. We're just figuring everything out. You know what I mean?
Okay.
Solve
No, I
reason
thought
for both, and I-
maybe we should
all who dies in the-
maybe we should jump to the conclusion and explain a bit more detail in the next class. I feel it's hard to keep the attention on for the 90 minutes, right? So if you know this connection, then x0 square will be equal to y0 square will be equal to z0 square will be, each will be half of what is end-to-end distance, mb square. And we know what all the lambdas are, so your delta S will be coming down to, again, will be 2mb square in the bottom.
And this is only for ideal elastic.
Yes.
Okay.
It will be ideal elastic. It's also is incompressional in unidirectional pull. So this happens if you take a natural rubber, put on the instrong, you start to pull it, what you would get. Before you pull the chain, that's what is that, x, y0, y0, z0 would it be? Okay. So this will be equals to lambda x square multiplied by 3mb square plus the same thing, lambda y square minus 1 So, for the single strand, if you put the value we had, what you would get is as simple as lambda y lambda y square, okay? That's basically the length square. And lambda x is square will be 1 divided by length. And because we have two of them, a pair, so that was converted to 2 divided by lambda. And we have 3 minus 1. Each one adds up and become that. So why this matters, now we saw for a unidirectional pulled rubber band, what would be the delta S versus the draw ratio? Okay? You can even do one more simple step, and it will be the last equation for this class. Okay? Well, we talked about at the beginning, you can get the force. Theoretically, you know what the force will be. Using the entropy partial derivative of lambda, L, or basically L is lambda in this case. What you would get is KT lambda minus lambda squared divided by. Why this is the case? If you take a derivative of this to lambda, what you would get is right here. Okay?
And again, that's only for ideal elastics.
Right. So, what this equation tells you, if you plot force versus lambda for ideal elastomer, that follows this equation. It's not a linear for the rubber band, okay? If it's just a hook spring, you know, the lambda and F will be just a linear relationship. But for polymeric material, we have this second term